In this video, we'll be looking at NQueen problem. Let me give you the problem statement. You are given an n by n chessboard and you are asked to place NQueen in such a way that none of the queens attack each other. Well, this is what we call the NQueen problem. In this video, we'll try to solve this using an algorithm. In computer science, there are various ways to solve these kind of problem, but in this video, we'll be looking at a specific technique called backtracking. In backtracking algorithm, the idea is to place queen one by one in different columns, starting from the first column in the first row. Every time we place a queen in a column, we check for clashes with already placed queens. So every time we find a safe column in a row, we add this position to the solution space and proceed to the next row where we repeat the same process again. So if we don't find such a column due to clashes, then we backtrack to the previous row and try to find another spot for the previous queen and revisit the next row. We repeat this until we place all the n queens safely. So if we can't find safe spots for all the queens, we stop our search and conclude that n queens cannot be placed in the given board. You might be thinking whether such a scenario exists. Well, yes, it exists if the chessboard is 2 by 2 or 3 by 3, where you can't place all the queens safely. So before we proceed to the algorithm, let's try to solve this manually. Let's try to solve this for a 3 by 3 chessboard first. But let me tell you upfront that there is no solution for this 3 by 3 board, but it gives you an idea of how we solve this problem. We begin from the first row, first column. Since it is the first queen, it is safe as there are no other queens to challenge it. So we add 0, 0 to our solution space and move to the next row. 1, 0 is not safe as it is under attack from the first queen. So we try the second column. 1, 1, it is diagonally under attack from first queen. So we try 1, 2, this is safe. Since we found the safe position for second queen, we add it to the solution space and try to move to the third row. 2, 0 is directly under attack from first queen. 2, 1 is diagonally under attack from second queen. 2, 2 is directly under attack from second queen. So we cannot place the third queen. So what we do is we backtrack. We try to find another position for the second queen, but since second queen is also in the end, we cannot move it further. So we backtrack. So we backtrack to the first queen. We move it to the second column and try to place the second queen. 1, 0 is diagonally under attack. 1, 1 is directly under attack, and again 1, 2 is diagonally under attack from first queen. So we again backtrack. We place the first queen in third column and we move to the second queen, and 1, 0 is safe. So we try to place the third queen. 2, 0 is not safe. 2, 1 is not safe. 2, 2 is also not safe. So we again try to backtrack. We try to move the second queen to second column in second row. It is not safe as it is diagonally under attack. And 1, 2 is not safe. So we backtrack again. We try to move the first queen to another position, but it is not possible as it is already in the last column. So we conclude that there is no solution for this 3 by 3 chessboard. Now let's try out solving a 4 by 4 chessboard. As we did for the 3 by 3, we begin from the first column in first row. Then this is directly under attack from first queen. This position is also under attack. It is safe here. So we move to the third queen. This position is directly under attack from first queen. This is diagonally under attack from second queen. This is directly under attack. This is diagonally under attack. So we backtrack. We move it to the fourth column. And then third queen is not safe in 2, 0. It is safe in 2, 1. So we move to the final queen. 3, 0 is under attack from first queen. 3-1 is under attack from third queen. 3-2 is diagonally under attack from third queen. 3-3 is directly under attack from second queen. So we backtrack. We try to place the third queen here. It is not safe. It is not safe. So we again backtrack. Since second queen is in final position, we can't move further. We backtrack. We try to place it here. We try to place the second queen here, which is not safe. Not safe. Not safe. Safe. So we place it there. We try to place the third queen in first column, which is safe. So we move to the final piece. 3-0 is not safe. 3-1 is not safe. 3-2 is safe. Since we found safe position for all the 4 queens, we conclude that we have obtained the solution. Let's design our NQueen algorithm. The first step in designing our algorithm would be to decide on the inputs we provide to our algorithm. So for this algorithm, we need to know the size of the chessboard. We'll use n to indicate the size of chessboard. Then we need to know the current queen positions. It will be an array, say queen positions. Then we need to know the row in which we are trying to place the queen. So row will indicate the row in which we are trying to find a safe column. Now we know the 3 parameters. Let's see if we can apply some constraints. It will be useful during implementation. So size of the chessboard, the constraint would be it has to be non-zero and positive. Queen position, its length cannot be greater than n, and it will be initially empty. Then row, which should always be less than n. Suppose we are following a zero based indexing, it cannot be equal to or greater than n. It should always be less than n. So our algorithm would look something like this: NQueen. So n will be the size of chessboard. Queen positions will indicate the position of the queens. Row will be the row in which we are trying to find a safe spot for a queen. So initially queen positions will be empty, row would be 0. The first thing we do inside this algorithm is we'll check whether the queen position is filled with n number of queens. If that is the case, it means that we have a solution. So we just need to print it and return true. This is what we call as the base case. Since NQueen is a recursive solution, we always have this base case which decides whether we should terminate execution of NQueen or not. So if this constraint is not satisfied, we'll iterate from the first column to the last column. We'll check whether the current position is safe with respect to the current queen placements. If it is safe, we'll add that position also to queen position, and we recursively call NQueen, which would in turn perform these things, and it will return either true or false. So if solved is true, we return true. Otherwise, we remove the current position and we continue to the next column. So this step indicates our backtracking. That is, we are removing the current position and we are looking for another position where we find a safe spot. And finally, if this iteration couldn't find any safe spot, then it will return false, which will be handled accordingly by one of the parent calls. What you see right now is actually a React implementation of our NQueen algorithm. You can see that NQueen method accepts value for n, queen position as array, and row as arrow number. So this is our base case, and we have our loop here, and finally the case for false, it is given here. We skipped discussing isSafe method. So basically this is the isSafe method, which checks the given position against all current queen positions. Basically it checks whether the diagonal value matches with any of the queen, diagonal or x value or y value. So you just need to go through this method. It is really simple. Basically it computes the value for d1 and d2, which is position dot x minus position dot y and position dot x plus position dot y, and we do the same for other queen positions, and if any of the values matches, it means that it is directly under attack. So let's simulate this and see how it goes. Let's look how we solve the NQueen problem for a 5x5 chessboard. You can see the backtracing and all in this simulation. The code has been done in such a way that it backtracks. Maybe we should look for a larger chessboard, say 6. See, you just saw the backtracking. This backtracking again. We backtrack until we get a optimal position which satisfies our constraint that none of the queens are under attack. And finally we have the solution.